Hello, everyone. My name is Sung Ho. I'm assistant professor at KTH and Notita. First of all, I would like to thank the organizers for inviting me to this very nice special conference. And also, I would like to apologize for not being able to be here physically. So today, I'm going to talk about the potential and pitfalls of flow matching for probabilistic forecasting of dynamical systems. And this is based on our recent work with my PhD student, Susan, and my collaborators, Ben, Michael, and the others. So in journey modeling, the main goal is the following. Given RID samples from some unknown probability distribution, we want to construct a sampler for hopefully the same distribution. And in this business, there are three main aspects that people care about. First, the quality of the samples. Okay, this can be measured by various metrics like FID for images and others. The second is mode coverage or diversity. So ideally, we don't want the samples to be a little diverse and not to resemble those from the training set. And lastly, it's about efficiency of the sampling. Ideally, you want to do the sampling as fast as possible to reduce the computational cost. And in the literature, there are many different models for generative modeling. For example, VAEs, GAMs, normalizing flows, and more recently, there are diffusion models and flow-based models. And in this talk, we are mainly focusing on flow-based or flow matching models. The main idea behind flow-based model is that first we construct or define some deterministic or stochastic map. And in flow matching, usually is this deterministic map that transport from noise to data. So we are interested in constructing some map from some, say, base or noise distribution to a given target or data distributions. And then once we have this transport map, we are going to use some parametric models like neural networks to learn this transport map. And the idea here is that we can do this via dynamical system. So we can build this transport map via, for example, ODEs. So let P0 denote our base distribution, P1 our target distributions. Okay. So the goal here is that given finite number of samples from P1, we want to construct a good scheme, right, that can generate new samples from P1. Okay. So whatever good means. Okay. And in our probabilistic forecasting case, good here means that we want a model that gives us a good probabilistic forecasting model as measured by appropriate metrics. Okay. So there's this broad paradigm of dynamical measure transport viewpoint, which says that we can construct this map using ODEs. Okay, so here it's driven by some time-dependent velocity field denoted as VT, and the ODE dynamics is on finite time interval, right, 0 to 1. The initial condition is usually sample from some base distribution, for example, just a standard Gaussian distributions. So once we construct this ODE, we can integrate it to some terminal time t equal to 1 to obtain samples. Okay, but here I didn't tell you what this specific velocity field is, and in fact, there are many different ways we can construct the ODE dynamics in such a way that many different dynamics will share the same endpoints. Okay, so there's a degree of freedom regarding how we choose the velocity field here. Okay, so there are two distributions, right, from this ODE. So first is the Eulerian distribution. So we can look at the evolutions of probability densities. We specify this continuity equation. And on the other hand, there's this Lagrangian point of view. We can look at the vector field that drive this ODE and also define the associated flow map. Okay, and once we have this, the probability path is simply obtained as a push forward. So you apply push forward operations on the base distributions. And then sampling again is just by integrating the ODE from t equals 0 to t equals 1. And the simplest example would be, for example, take the base distribution to be Gaussian, standard Gaussian, and the target, okay, let's say we have artificial one like a bimodal Gaussian in 1D. And in this simple case, we can even write down explicitly one particular example of this polypath that realize this transport map. Okay. And so, as I said just now, the construction is non-unit in the sense that we can have different dynamics or different ODE dynamics that can lead to the same probability path, as illustrated by this example on 2D. And in this case, in fact, we have like infinitely many dynamics that can lead to the same probability path. Okay. And here we are interested in flow matching. So in flow matching, polypath is piecewise. So we first choose this polypath. We are not going to optimize it. We choose it, and then we are going to uh, yeah, we're going to deal with the rest. Okay. So assume that we choose this. And let B denote the velocity field that generate this polypath PT, right? We are discontinuity equations. Then in practice, what we do here is that we approximate the velocity field by some parametric model like neural networks. Okay, and this is simply by minimizing these regression loss. Okay, so what's specified is a polypath, and what is learned here is the velocity field. Most ODE generates samples at inference time. And it turns out that there's a way to do this in a simulation-free manner, in the sense that during training we don't have to integrate ODE from t equals 0 to t equals 1, and the simulation is only done during inference, right, when we do the sampling. And so all this sounds good, right? So let me give you some examples of probability path, right? So how we pick the probability path? A canonical choice or a popular way to pick this in the literature, at least, is via these linear interpolations. So here we have random variables, right? S0, X1, right? Distributed from P0 and P1 respectively. So this basically is just a straight line interpolating from between S0 and X1, okay? And this gives us the probability path PT, right? And if we differentiate this respect to time, we end up with this conditional velocity field. And for this simple example, it's just a constant velocity field. So remember, this is conditional on the random variable x0 and x1. So if we look at the conditional expectations, so we have this marginal velocity, which is our target to learn, right, in the regressions. And this is in general intractable, right? And we need to find a good way to approximate this approximate this conditional expectation. And so there's this nice framework called conditional flow matching, or CFM, that can allow us to do this in tractable, efficient manners. So the idea here is that so make things a bit more general. So let's say we introduce some latent variable C distributed from some distribution pi independent of the t, and then we choose a target conditional path, right? We pick this probability path that is conditional on this latent variable C. Okay, and once we have this defines the corresponding velocities and also fully determines the marginal probability path, right? Which is this mixture here. And then the induced marginal velocity field is this conditional expectations. Okay. And in CFM, we train a neural network by regressions against these conditional velocities. And because this, so remember this V is conditional on C, and C usually, say it represents some data sample. So we can have a per sample computations of these conditional velocities. So it makes the training tractable and efficient this way. So during each iteration, basically we sample a t from some uniform distribution from 0, 1, and we sample from a latent variable c, for example, just from the data samples, using data samples. And Yeah, and then we also simulate, we also sample the ZT. And turns out that minimizers of this CFM loss coincide with the minimizers of the FM loss. Okay. And remember earlier we talked about this latent variable C, right? And the standard example would be to take C to represent the data sample. So this is usually the case for images. But in our time series case, we can take this latent variable to represent a transition pair from that we extract from the time series. Okay, so this is the thing that we will look at a bit more closely later. But for now, let's actually look at a few more examples just to get a bit of intuition. So a simple example is what people call rectified flow model, where the base distribution is taken to be standard Gaussian. And the latent variable is simply representing the data, right? So this is our target distribution from coming from target distribution. And the probability path here is simply a Gaussian probability path with variance of 1 minus t squared. And from here, we can also derive the corresponding velocity field, which is basically a rescale displacement field. Okay, so it is rescaled by 1 minus t here. And it turns out that this rectified flow constructions has led to efficient algorithms for high dimensional image generation. Another example is slightly more general. So instead of considering the Gaussian base distribution, we can in general consider base distribution coming from arbitrary distribution. Let's say the distribution has some probability density function PDF k. And then if you look at a fine conditional flow defined by this flow map, okay, then we can understand or derive the density via change of variables. And it turns out that we can also derive the conditional velocity field as the following, right? So this is basically a fine in Z. And the earlier rectified flow example, in fact, is a special case of this. Okay. So these are two examples. So now going back to flow matching for sequential data, right? So we want to understand whether applying the idea of flow matching for policy forecasting, whether this is making sense or not for time series forecasting, and how can we actually construct such a flow matching based model for forecasting, and also understand the potential and pitfalls of this type of models. And then once we have these models, we also want to understand the inductive bias, right, of the forecaster, and also the related implications. So the setting is the following. So let's say you are given trajectories, right, of so basically some time series set, and then the idea of policy forecasting is that so given say the past k elements, right, we want to predict not the point but the distributions, right, distribution of the future L elements. So we are interested in basically predicting the conditional distributions of the future given the past. And so the neural network, you can either train it on the original data space or on the latent space. But for later, we are going to talk about PDE forecasting tasks. So for dimensional reductions, we are going to actually train the neural network on latent space. So this is just a head start on why is this a latent space here. Okay. So now a fundamental question is how we should pick this poly path, right? So as we discussed earlier, this depends on this will require us to first pick a poly path before we can apply the flow matching method. So how are we going to do this? So in particular here, we are going to look at the case when the latent variables, they represent transition pairs. So in fact, let's say given time series training sample set, we can collect them into a set of all transition pairs like this. And then we are going to consider the following family of Gaussian probability paths. Okay, so the main is basically some linear interpolations of linear combinations of the transition pairs. And also the variance is some time-dependent function. So there are some choices I need to make regarding AT, BT, and CT. And here are some choices that can connect to the diffusion model literatures. But we actually want to find the choice, ideally optimal choice for our probabilistic forecasting task. Okay, so this is so here I already given out our the formula for our choice of the coefficients, and I will walk you through how we motivate these choices here. Okay, so how we choose AT, BT, and CT. So the motivation is the following, right? It goes back to Schrodinger's thought experiment in the 30s. So the idea is the following. So let's say we observe a cloud of large number of independent Brownian particles evolving in time, say from t to 0 to the 1. And then say we have observations at t to 0 and t to the 1. From this, we basically have empirical distributions, right, at t to 0 to the 1. And then let's say that these distributions, so let's call it them rho 0 and rho 1, they are not compatible with the law of large number in the sense that this identity does not hold. So this must have mean that the particles has been transported in some unlikely way. The Schrödinger then asks, out of many unlikely ways in which this could have happened, which one is the most likely one? Okay, and it turns out that you can formalize this problem as basically the problem of finding the optimal stochastic process that evolve a given measure into another. Okay, so rho 0 to rho 1 in the Schrödinger case, subject to marginal constraints. So marginal constraints is that in our case, that at t equals 0 and t equals 1, it has to match the empirical distributions. Okay, subject to these constraints and also based on some prior belief. So our prior belief is that the dynamics are Brownian. Okay, and more mathematically, you can actually phrase this as some KL minimization problem. So basically, it's a constraint minimization problem over all path measures that are subject to marginal constraints, say at t equals 0 to 1. So here P0, P1. And then we are minimizing this KL divergent aspect to some base or reference path measure. So in the Schrödinger case, this would be Q here would be a Wiener measure. Okay, so this is how we can formalize this problem. And in our time series case, we are interested in not mapping point to point, but mapping distribution to distribution. And in particular, we are interested in map from Gaussian around current state to Gaussian distribution around the next future state. Okay, and we want to basically find what is the most likely path that map these two Gaussian distributions. Okay, so this is for our time series case where we use the transition pairs. Okay, and it turns out that for this so-called Gaussian SB problem, right, we have closed form solutions for this problem, and is given by this theorem, right? In fact, the solution to the Gaussian SB is a path measure of some Markov Gaussian process, with where the mean and variance we can write down, and it's given by this. And if we just apply this result to our time series case, right? So remember the constraints there is basically there are Gaussians around the current time series state and Gaussian around the next time series state at the next step, right? So if you just apply this, then we end up at this choice of AT, BT, and CT, and in particular, CT is given by this formula, so it's quadratic in T here, and with the minimum variance of sigma mean square and the maximum variance happening in the middle of the path, right? In the middle of the path, and from here we can also derive the corresponding vector velocity field that define the flow, which is given by this. So this equation fitting, it will serve as our target velocity field to regress against for our task of probabilistic forecasting. Okay. And it turns out that this SB problem also has some neat interpretations in terms of minimization of some expected cost functional, involving kinetic energy, feature regularization terms, and drift alignment with the score functions. Okay, so these are some extra like nice interpretations that these SB problems have. Okay, so good that we now that we know what are the optimal choices of AT, BT, and CT for our probabilistic forecasting task, we are going to basically uh, train a neural network to learn this, right? And let's see how our method would do for PDE forecasting tasks. So in particular, we are going to compare our choice of polypath with other choices of polypath and see how the forecasting performance compare. So we look at tasks such as fluid flow past a cylinder, shallow water equation, diffusion reaction equation, Navier-Stokes. So these are basically high dimensional dynamics tasks. And for dimensional reduction reason, we will train the neural network on some latent space. Okay. And it turns out that design choice of polypath matters a lot. And if we compare our choice of polypath with the others, if we look at say test MSE, so our method actually has the like one order of magnitude lower in test MSE compared to the other methods. Okay. So it matters a lot, and also if you look at correlation coefficients, our method has slower decay, lead to slower decay of correlation coefficients compared to the others. And also during training, our choice of only path actually lead to faster conversion and smoother loss curve. Okay, and here are some visualizations of the forecaster dynamics. So now that we understand how to pick AT, BT, and CT, right, can we further understand what is the inductive bias, right, of this associated with this particular choice of probability path? And in particular, so when we try to apply FN to say for positive forecasting with this particular choice of probability path, so what is this velocity field, right? What is this optimal velocity field that our neural network is trying to optimizing for, right? So we try to understand this in the setting of let's say we are given a finite number of data samples. So in which case we can instantiate the target distribution basically as this empirical measure, and then from here we end up with this empirical CFM objective, and remember this is square loss, right? And turns out that for this in this setting we can derive the optimal velocity field, right? Or solution to the regression problems. And the optimal velocity field, it has these closed form expressions. So basically, it's weighted linear combinations. It's a weighted combinations of some instantaneous velocity field with weights given by this formula. So essentially, the proof relies on some applications of the Bayes rules. And so this formula might be a bit too complicated to look at, but if you look at the going back to the rectified flow example earlier, we can write down explicitly the optimal velocity field, and it looks like this. So remember earlier we saw something like x minus z or 1 minus t. So here in this so in this the optimal velocity field here, it basically is a weighted combinations of this thing, but it's a per sample thing, right? Xi instead of x, and weights wi given by some softmax functions. Okay, so it has some pretty nice interpretations, right? It's some time-dependent weighted average of the directions pointing towards the empirical samples. And we can do the same thing for the affine flows, right? And similarly emit similar like structure in for the optimal velocity field, and you can see some like similarity with Nadaraya-Watson kernel density estimators here. And in our time series case, we are also asking the same question. So we our particular choice of the path, right? So remember we work with transition pairs, and then this is our our choice of probability path that we pick. So for this one, so what is the optimal velocity field that we get here, right? So it turns out that is given by this formula. So the optimal velocity field consists of two components, right? First is a linear term that has a time-dependent coefficient gt, like this, and then a non-linear term, which basically this is a vector combinations of some yj, and yj you can think of this as some correction terms, and then weights alpha j again has some softmax structure here. So in other words, the velocities decomposes into a global linear term and a local data-dependent non-linear term weighted by Gaussian kernel attention. Okay, and then furthermore, we can understand this get some more interesting interpretations by looking at decompositions into two terms like this, right? First is a transition replay terms in the sense that this is a better combination of the sort of like a finite different approximations of velocities using the samples. And then the second term is a score correction terms in the sense that this term can be related to um, the score functions, empirical score functions. And so remember here there's a GT, right? So if sigma goes zero, then the learn dynamics basically overfix by performing hard transition lookup. All right, so akin to memorizations. Whereas for like positive sigma, right, it controls or induce kernel smoothing and regularizations that promote generalization beyond the training bridges. So this sigma basically controls some sort of a trade-off between memorization and generalization in this time series setting. Okay. So now we know that these flow metric models for forecasting, they are not just doing what we call transition replay, but they could go beyond this by applying some score correction terms. Okay, so now that we have this V head start, right? So why don't we just use this, right? And use them as a forecaster. So remember here, this does not involve any neural network, so we don't have to train a neural network here, right? We just use this, but this term it depends on all the training samples. Okay, but we can use this in a training-free manner. So this is what we call training-free sampler, and we just plug this V hat star into the ODE, integrate this, right? So given initial condition, which is Gaussian around current state, you integrate this to t equal to 1 to get samples that will tell you the estimate or the forecast at the next future time. And so you get your forecast, and then you can do this many times, you get ensemble of forecasts, and then you repeat this by integrating the OD again using the initial conditions from the predictions, right? And then you get multi-step forecasting this way. Okay. So here is a schematic of this training-free model, which we call free FM. Okay. So now, so I will just skip this part. There are more results that we can look at, but I want to basically tell you how effective or how not so effective, right? Free FN is, right? So we are going to look at low dimensional forecasting tasks, and we will look at the benchmark of DYSTS. Okay, so this is a chaotic time series benchmark created by Gipin et al. Consisting of 135 chaotic OD system 3 to 60 with aligned dominant time scale and standardized integrations. And then we evaluate at long horizons and also so we look at both like long horizons and also distributional evaluations, right? So it turns out that this training free model, free FM, it can even outperform neural network trained model for this particular like simpler, like low dimensional forecasting task. And the same for if you look at say other metrics like CRPS, which is more relevant for probability forecasting, 3FM can also do better than the neural network trained models. And then in terms of long-term attractor reconstructions, we also have the similar result, perform better. So this is for the caveat here is that this is for low dimensional chaotic time series data. And in general, 3FM has cursor dimensionality, right? So it becomes harder if you want to scale this well to high dimensional time series setting. Because after all, if you look at the form of the velocity field itself, right, it has some kernel. It's really some kernel based methods, right? And so it's also subjected to curse of dimensionality. Okay, so just to summarize, right? So in this talk, we look at flow matching as a broader as an example of a broader dynamical measure transport framework. And can we apply flow matching to forecasting? Yes, but we need to understand that it's very sensitive to a choice of probability path. However, we can use the idea of surrender bridge or dynamical optimal transport to construct an optimal probability path that perform well for policy forecasting, even for high dimensional PDE dynamics. Okay, so once we understand how to pick this probability path, we then understand what is the inductive bias of this particular choice of probability path. And then using this lens of empirical FM, right, we show that the FN sampler, they are actually optimizing for a non-parametric, non-memory augmented OD. And as a bonus, this gives us a training-free forecaster that we can test against other models. And for at least for the low-dimensional forecasting, low-dimensional chaotic time series tasks, this free FM model it worked pretty well. Okay. So that's all for today. Thank you so much for attention.